Good morning, friend. Myself Jitendra Kumar. In continuation of lecture on electrical machine design, today we are discussing about the machine construction feature. Under this, in the previous lecture, we already covered some parameters of the major consideration design of electrical machines of electrical engineering materials. We are just continuing about this. First parameter over here, it will be the saturation. Because there will be some design limitations are there. In the previous lecture, we are just designing about the machine that how the machine will be designed over there, what are the limitations, what are the parameters we have to focus under this, and now we are discussing all the limitations. That what are the limitations are there because whenever we are just thinking about to design any machine, we are just concerned that the machine will be close to the ideal nature. But what happened? The ideal one means we are not looking over the things which will be associated over there. So we have some limitation related to the materials, related to the environment, related to the components which we are using because there is a mechanical components are there. So in theoretical we are making any kind of components are there that it must be there and we are just implementing this and it will be the size of the machine is there. But the mechanical concepts are there, so we have to just concentrate that what are the limitations of the size, what are the limitations of the electric current. Whenever we have to just deliver the electric current, it will be associated with the how much current is there, what is the limitation of the winding, what will be the limitation of the insulations are there. So another parameter it will in the design limitation there will be the saturation. Electromagnetic machines use ferromagnetic material. Under the normal condition, we are opting the ferromagnetic material for the electromagnetic purposes. The maximum allowable flux density to be used is determined by the saturation level of the material used. So it will be defined about the limitation that because up to a maximum limitations of that material, it will be defined. So the saturation level is there. So whenever we have to just increase the amount of the current, then the automatically it will be close to the saturation. Once it will be close to the saturation, then there is no upgradation in the MMF produced or the flux produced by the material. So it will be the first limitation is there. High value of flux density results in increased excitation, resulting in higher cost for the field system. So there is a maximum limit about this, and whenever we have to use the a material having the high flux density value, then it will be automatically affected over the field system. So the field system must be so strong that it will be absorb the value of the increase in the flux density. Then the saturation is the state reached when an increase in applied external magnetic field. H cannot increase the magnetization of the material further. So the total magnetic flux density or the more or less levels of. So the H parameter and the B parameter. H parameter will be associated with the current and the B parameter will be associated with the voltage. So whenever we have to just increase the current, then it never linked to increase the value of the flux density. So the flux density it will be increased irrespective of the external magnetic field. So ferromagnetic materials like iron are composed of microscopic regions called magnetic domains that act like tiny permanent magnets that can change their direction of magnetization. Before an external magnetic field is applied to the material, the domain's magnet will be changed. Fields are oriented randomly, effectively cancelling each other out, and so its magnetic field is negligibly small. When an external magnetizing field H is applied to the material, it penetrates the material and aligns the domains, causing their tiny magnetic fields to turn and align parallel to the external field. It will be reflected in the form of a wave, in the form of a picture in the next slide. Adding together to create a large magnetic field B which extends out on the material. This is called magnetization. The stronger the magnetic field edge, the more the domains align, yielding a higher magnetic flux density. The saturation occurs when practically all the domains are lined up, so further increasing H cannot increase B beyond the increment that would be caused in a non-magnetic material, or in other words, cannot cause further alignment of the domains. It will indicate it over here. We are finding that at the initial stage, all the ions are distributed or randomly distributed within the material. Once we are given a high tension or the supply over there, then it will be try to reorient it in a particular direction, further increasing in the tension or further increasing in the current. We are finding that all the ions which will be initially randomized in nature, now it will align in nature. So the formation of the magnetic domain, it will indicate that once all the ions are in a particular direction or aligned in a nature, then they further increment in the edge. There is no impact over the flux density. So the B will be fixed once all the ions are in a particular or in a unidirectional in nature. The magnetic domain is a region within a magnetic material in which the magnetized is in a uniform direction. This means that the individual magnetic moments of the atom are aligned with one another and they point in the same direction. When cooled below a temperature called the Curie temperature, the magnetization of a piece of ferromagnetic material spontaneously divides into many small regions called magnetic domain. The magnetic domain structure is responsible for the magnetic behavior of ferromagnetic materials like iron, nickel, cobalt, and their alloys, and paramagnetic materials like chloride. This includes the formation of permanent magnet and the attraction of ferromagnetic materials to a magnetic field. The regions separating magnetic domains are called domain walls, where the magnetization rotates currently from the direction in one domain to that in the next domain. The study of magnetic domains is called the micromagnetics. The temperature rise, the most vulnerable part of the machine is its insulation. Because the temperature rise is will be associated with the insulation, that which type of insulation we are providing, it will try to release the heat from of the conductor which will associated over here. Then the temperature rise will be low. Once the heat is never released from the insulation, then automatically the internal temperature will be increases up to a level. The operating life of machine depends upon the type of insulating material used in its construction. So the material which we are using for the insulation, it also helps in deciding the life of the material, because whenever it never release the heat, then automatically the life of the material which will be conducting the current, it will be heat up. So automatically the life of that material will be reducing. Also the life of the entire machine, it will depend upon the insulating material, which type of material we are using, and what will be the nature of the material it will be offered. The life of the insulating material in turn depends upon temperature rise of the machine. How much temperature rise is there. If an insulating material is operated beyond its maximum allowable temperature, its life is drastically reduced. Means it will be exponentially reduce the life of the material. If we increase the temperature, if we increase the supply of the current will be increases, then automatically the heat will be increased. Heat will be increased means temperature will be increased. If that temperature is beyond the insulating material range, then it will be reduce the life of the insulating material, and automatically the insulating material life will be reduced, and automatically it will develop a tolerance to the entire machine. Insulation, the insulating material used in a machine should be able to withstand the electrical, mechanical, and thermal stresses which will be produced in the machine. The mechanical strength of the insulation is particularly important in the case of transformers. Large axial and radial forces are produced when the secondary winding of a transformer is short-circuited with the primary on. Therefore, while designing the insulation of a transformer, due consideration must be given to the capability of the insulation to withstand large mechanical stresses that are produced under short-circuit conditions as apart from electrical and thermal breakdown considerations. The type of insulation is decided by the maximum operating temperature of the machine. The size of insulation is not only decided by the maximum voltage stress but also by the mechanical stresses which can be absorbed by the insulation. For example, for the same operating voltage, thicker insulation has to be used for large size conductors than for a smaller size ones. Efficiency. The efficiency of a machine should be as high as possible in order to reduce the operating cost of the machine. To design a high efficient machine, the magnetic and electric loadings used should be small, and this requires the use of large amount of material, both in iron as well as copper or aluminum in nature. Therefore, the capital cost of the machine designed for high efficiency is high, while its running cost is low. Mechanical parts of the machine, the construction should be as simple and economical means with as little labor as possible. The design of mechanical parts is very important in the case of high-speed machines. For example, while designing a turbo alternator, the rotor dimensions are so selected that the mechanical stresses at the bottom of the rotor teeth do not exceed the maximum allowable limit. Turbo alternator, we are seeing that turbo alternator means if the rotor is rotating more than 3000 rpm, then it will come under the turbo category. The induction motors, the length of air gap is kept as small as possible in order to have high power factor of the machine. The size of the shaft should be such that it does not give rise to excessive unbalanced magnetic pull when deflected. The shaft of the machine should be short and stiff, so there is no significant deflection of the shaft and hence the unbalanced magnetic pull is small and is within the manageable proportion. In large machines, the size of the shaft is decided by considering the critical speed, which depend on deflection of the shaft. Bearings of the machines are subjected to the action of rotor weight. The capability of the bearing will be defined about the rotor weight. What will be the weight of the rotor? What type of external loads are there? Inertia forces due to unbalanced rotors and forces on account of unbalanced magnetic poles are there. The type of bearing to be used in a machine are decided by considering the above mentioned forces and also the type of construction, whether the machine is horizontally or vertically mounted in nature. Then another parameter is the commutation. The problem of commutation is important in the case of commutator machines, where we are using the commutator. As commutation condition limits the maximum output that can be taken from a machine. For example, the maximum power of a single unit DC machine is approximately 10 megawatt, and this limitation is only on account of the commutation difficulty because commutation means the conversion of the AC supply into DC supply or DC supply into AC supply. So, what type of material we are using for the commutation? It will be defined about the capability that how much capability is how much the device is capable to commutate or convert the AC supply into DC or DC supply into the AC one. Power factor. Power factor results in larger values of current for the same power and therefore larger conductor sizes have to be used. This problem of power factor is particularly important in the case of induction motor. The size and hence cost of induction motor can be reduced by using a high value of flux density in the air gap. But this results in saturation in iron parts of machine, and consequently a poor power factor will be associated with the induction machine. Thus, the value of flux density used depends upon the power factor, and hence the power factor becomes a limiting factor for the induction machine. In fact, the length of the air gap to be provided in an induction motor is primarily determined by the power factor consideration. Consumers specifications are the important parameters over here, because the consumers are the buyer of the machine. So whenever we have to make the machine, but that machine is compatible to the consumer. The limitations imposed by the consumer's specification on the design of electrical machines are evident. The specifications are laid down in the consumer's order have to be met, and the design evolved should be such that it satisfies all the specifications and also the economic constraints imposed on the manufacturer. Then the standard specifications are there. These specifications are the biggest strain on the design, because both the manufacturer as well as the consumer cannot get away from them without satisfying them. So this will be the end of the lecture, which will be associated with the design of the machine. So in the next lecture, we are just continue about the previous part, and we will discussing about the another parameter which will be associated for the design of the electrical machine. Thank you.